Hey guys, recently I've shown you these beautiful artisan control cabinets that Spinergy makes to support their CNC spindles with state-of-the-art, made in Germany electrical work. They are so nice, safe, extendable and maintenance-friendly. Meanwhile, the rest of my machine is still run by this hazardous flying spaghetti monster. If I have to plug in a USB drive into that raw, dangling motherboard, I kinda have to put my hand in there and hope not to get shocked by any exposed live wiring. Disgraceful, but today we are finally going to fix that. I've also preached a lot about a wonderful communication technology last year. One which is able to coordinate real-time motion control and more, using nothing but normal computer network interfaces and cables. Other than preaching, I haven't done a lot with it yet though, so this will also be my practical EtherCAT debut. We will prepare a compact new cabinet and then densely populate it with a Raspberry Pi. 4 axes worth of high-end Leadshine Servos and a bit more requisite hardware, all EtherCAT everything. And finally, we'll take it out on the road and give it a test drive. I foresee lots of quirks and features, but mostly significant improvements. This upgrade represents a quantum leap in motion control technology for me. The eldritch horror that was my previous control box started with me deciding to freehand YOLO it. I kinda made it fit because I had that huge cabinet. But it's really not much trouble at all nowadays to create a complete, accurate model based on 3D models that good manufacturers should be offering. That way one can meticulously plan and optimize a layout, ensure that cabling and air cooling fit, and that no servo drives are placed in the way of a door lock, of course. Still, this is going to be a tight fit in there. Slotted cable ducts will make things look super neat and tidy. These are a bit undersized, and that's going to make them a small handicap for modifications later though. The DIN rail will hold a circuit breaker, a mains filter, some distribution terminal blocks, and some back-off EtherCAT controlled in- and outputs. For interfacing with other components such as solenoid valves, and for closing the spindle's safety circuit. You may have seen this part before. It should be in the video before the last one. The rectangular holes are for keystone connector blocks. There will be Ethernet, HDMI, and a few USB ports. For the Raspberry Pi that will be running the show in here. The round holes are for cable glands. My servo drives should only require 2 cables per axis. But my plan for homing switches, or absence thereof, sounds a bit sketchy even to my ears, so I'll prepare another row of holes, just in case I need normal limit switches after all. I'm also engraving some cooling fan cutouts and an air inlet on the opposite side. I expect the servo drives to be reasonably energy efficient. But there are 1600 watt of output power squeezed into very little volume, so better safe than sorry. Can you guess where the front-facing on-off switch goes? That's right, it goes in a laser-cut square hole. And here are the stars of the show today. There was nothing specifically wrong with my old motion control system, for the record. It just had too many layers, making it unnecessarily complicated. There was LinuxCNC having to run on an ATX motherboard for its PCI Express slot. The software interprets G-code and plans movements ahead of time. These plans were handed over to a PCI Express FPGA card, on which PID controllers were keeping track of position feedback, while generating step direction impulses to steer the hardware in the right direction. Those impulses in turn were received and interpreted by another motion controller inside of the servo drives. But no side is even using step direction impulses internally. We were only going through all this trouble for a legacy interface. Now we are shedding all the middleware or glue logic or whatever, and instead let the Raspberry Pi talk to Leadshine's brand new EL8 EtherCAT servo drives directly through Ethernet hardware that is already ubiquitous. These new drives were only just released in 2023, so they are full with the latest and greatest features. One can kinda tell by the USB-C diagnostic ports. They are using faster clock speeds internally and have the highest digital signal processing power. For features such as auto-tuning in operation or dynamic vibration suppression, there is a gantry synchronization mode for running two motors side by side without them getting into a fight over minute details. They have more configurable I/Os, including analog ones, and a secondary encoder interface in case you want to use something like a precision glass scale, and a new safe torque-off capability that prevents motor movements reliably, in spite of any fault conditions with an electric disconnect, rather than just telling a microprocessor, hey, I have to crawl into the machine for a moment, please don't move right now, okay? I would prefer to keep my body parts attached if it's all the same to you. Newer silicon, of course, also comes with improved energy efficiency, so these 400-watt drives are significantly smaller than my old ones with equal power. Great for my compact control cabinet plans. The motors too actually, but I think that's just because of a more compact encoder compartment. I started planning this idea back when the Raspberry Pi Compute Module 4 was still the coolest Pi on the market. It will work, and with this WaveShare dual Ethernet baseboard, I am getting the perfect number of Ethernet ports, but I think nowadays I'd much rather choose a Pi 5. Additionally, I'm using a circuit breaker for the mains power supply. A two-stage EMI filter for the same. The servo drives have absolutely no EMI countermeasures. Some Phoenix distribution terminal blocks to spread out the mains power to all the consumers. A 24-volt DC power supply. Some configurable distribution terminal blocks for that one too. Two relays for not yet determined purposes. And finally some EtherCAT controlled digital I/Os in the shape of Beckhoff EL1008 and 2008. To be fair, normally these modules are a lot more expensive than the Mesa FPGA card that gave me universal in and outputs in the past. However, for a DIY project you can usually find them cheaply secondhand on eBay. That sounded weird. Along with each Axis servo kit, Leadshine has supplied 5 meters worth of wonderfully flexible, drag chain capable cables to survive millions of bending cycles without work hardening and breaking. In an industrial setting, this needs to be a special high-grade, finely stranded cable. It is, and I really enjoy finding such little details where a manufacturer shows that they know things too. Their shielded firewire-esque connector on the encoder cables is a bit too bulky to fit through cable glands or through heat shrink labels, but it can be disassembled pretty easily to make that work. Nice leads, I'm only sad that they aren't shiny. On the motor side of these cables sit really cool IP67 connectors. Really cool unless you are an assembly line worker who has to make these all day long. Love how they added pieces of heat shrink tubing to those pins associated with the low voltage motor brake that are a little bit too close to the high voltage motor pins. Again, great attention to detail, but one little thing is not accounted for as far as I can tell. The motor brake is nothing more than a big old electromagnet. When it is de-energized to lock a motor, its breaking down magnetic field induces a large back EMF. A voltage spike that can destabilize or even damage the sensitive electronics elsewhere in the system. To prevent that, it's desirable to have a reverse freewheeling diode as close as possible to the magnet pins, so I'm trying to squeeze one right into the connector here. As an option, these servo kits can be ordered with absolute multi-turn encoders and battery backup for those. A little clip-on 18650 cell helps the motors remember their absolute position for years, even if the machine isn't powered on. That way, practically you have to home your axes only once and then never again. I'm not quite sure what happens if a motor is moved while under battery power only. Are the encoders fully awake and ready to count 24/7? Or are we only keeping some volatile memory chip alive? We will investigate in a moment. EtherCAT makes wiring super easy. It's literally just a series string of devices, linked by network cables. Other than that, each servo drive needs 2 mains connections, one for the control logic and one for the power output. And of course the 2 motor connections, power and encoder, and that's it. For now, I'm not using any of the general purpose I/Os or the safe torque-off connector. Alright, time for a confession. I've talked a big game about my grandiose 3D model earlier. Unfortunately, I failed to take into account the cabinet's door lock height. So now we have a little bit of a conflict of interests here. Ooh, how awkward. I should just flip the layout horizontally. But I think I'll postpone that a little bit, just in case I find more mistakes that also need changing in the weeks to come. Let's talk about software. I said it before, we are still relatively early adopters of LinuxCNC EtherCAT, so the setup isn't a polished graphical user interface from start to finish yet. But the open source community continues to do magnificent work, based on which everybody can learn about and freely use a software package comparable in quality to those used in multi-$100,000 CNC machines. Specifically, what I'm using is an up-to-date LinuxCNC dev package, which comes with the dependencies needed to compile HAL components. On top of that, I'm installing the EtherCAT master as described by Rod W in the LinuxCNC forum, which is causing a lot of excitement in the status LEDs already. After these standard steps, we should already be able to run EtherCAT slaves in the command line to get a list of all connected conscious devices and their slave IDs. Furthermore, this is also enough to read and write standard backoff modules, like my 8-channel digital in and outputs. However, to take control of my Leadshine servo drives, a few more steps are necessary. They comply with a standard called CIA 402, meaning that the communications that have to take place for a motor to engage position control mode, to go somewhere, or to report its status, are compatible across a huge majority of manufacturers. That is awesome, because GitHub user dbrown1981 has taken the time to publish a LinuxCNC component to handle exactly this type of CIA 402 compatible drive. That worked too right away. Only my extravagant desire to use one of the servo drive's built-in homing functions needed a little bit more attention. I added some small delays to dbrown's CIA 402 component, I made a custom homing state machine for LinuxCNC, and I'm publishing everything, my whole machine definition and step-by-step instructions on GitHub. Again, these are optional flourishes. The battery-backed multi-turn absolute encoders can be considered homed always. But check this out, isn't that amazing? This is what Leadshine humbly calls homing mode -6. It limits speed and moves in one direction. As soon as torque above an adjustable threshold is detected, it resets the encoder position and indicates homing done to the computer, which can then switch back to maximum torque position control mode. This way we could, if we are brave enough, home all axes by driving against solid, rigid CNC machine end stops, eliminating uncertainties from electromechanical limit switches or inductive sensors, at no extra cost without additional wiring, without adding another component that wears out to a machine. Oh, and there are 36 other homing methods to choose from, with or without traditional sensor inputs, or with an optional retraction move after determining the home position. My choice in this case, -6, might leave a bit of residual strain in an axis. Alright, let's quickly test the encoder battery backup before we head downstairs and finally upgrade my CNC machine. In this preliminary configuration, one motor shaft revolution corresponds to 1 millimeter. Let's memorize that this one was sitting at roughly 1 millimeter before we cut the power. I have temporarily substituted the battery backpack with a Joulescope JS220 Precision Energy Analyzer, which is the perfect tool for testing ultra-low standby power devices such as this one. And ultra-low it is, 64 microwatt when unbothered, that's crazy. If we assume a 10 watt-hour 18650 battery, that would give us over 17 years of data retention time, or less if we move the motor shaft. I guess that means that it is indeed watching and counting all the time. These were approximately 2 shaft rotations in a random direction, so if we turn mains power back on, we should be seeing the x-axis at either 3 or -1 millimeter. And that is close enough, making that standby power consumption even more impressive. Holy moly. Alright, we're ready to go. By default, these motors are delivered with a keyed shaft. The key is in there with a very tight press fit. If you have to remove it, you can do so with this M3 thread, rather than trying anything risky and putting large axial forces on the shaft. 3D printed motor mounts, still there, still looking undignified as hell, but being absolutely unproblematic for many years. My Z-axis gets a motor brake now. I had this silly idea of getting perfect surface finishes by disabling any motion control loops for this axis and just making a finish pass with the brake engaged. It's technically possible for sure, but it will require specially prepared G-code. So not sure if worth the trouble. An adjustable gas spring to compensate for the Z-axis weight sounds a lot more attractive to me right now. The pneumatic valves for the spindle's tool changer will now be operated by two of Beckhoff EL2008's 24-volt outputs. The compressed air sensor that's also a part of Spinergy's pneumatic cabinet will be monitored by one of Beckhoff EL1008's inputs. Refined code in the GitHub repo below, as I said. Last time we saw a thermal expansion issue that kept the tool changer in my early version Spinergy X22 from returning home all the way, in some cases above a certain temperature. I've since sent the patient home for an adjustment and was very happy to have received it back fully healed after only 3 business days. That was a pleasant surprise by the Spinergy team, but now I've just bumped into 2 new quirks that I need to address before moving on. Normally, these Omron MX2 inverters go only up to 400 Hz output frequency. To suit the needs of the 4-pole motor in my X22, Spinergy have fitted a high-frequency version of this inverter in the control cabinet, which goes all the way up to 1 kHz. That works great with normal analog voltage control, but when using RS485 digital controls, which of course I passionately prefer, the register for the frequency command is just 16-bit wide. And it overfloweth if I write anything above 655 Hz. Haha, wouldn't want to plunge into a workpiece like this. A solution was not super easy to find, so I thought I'd quickly mention it here. I'm now using a kind of internal math operator with these settings to double the commanded frequency. And now we are reaching 1000 Hz, aka 30,000 RPM. Nice. And of course, RS485 communication comes with a lot of free diagnostic data in tow, such as motor load or inverter temperature. And the last issue was a bit easier to spot, simply by looking at the difference in sizes between the EMI filter that Spinergy used in their X-Control E versus the sad little budget option in my cabinet. Let's say we have a not isolated RS485 cable going from one cabinet to the other. Where is the VFD's EMI going to go? Is it going to bend itself backwards to squeeze through the highly effective EMI filter? No, of course it's going to choose the easy way, through my RS485 adapter, and into my system, where it's going to disrupt pretty much every low-voltage consumer. So yeah, that link needed some optical isolation, of course. And that is finally all the preparation, for now.
Shake, 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 Sonora, shake your body liner. Somebody help me!
Our new servo drives might still need some manual fine-tuning, depending on how well Leadshine's online auto-tuning algorithms work.
Work, Sonora!
But maybe not today. Let's give them a try first. The wobbles that are visible here quite clearly are just my tripod sitting loosely on the T-slot plate. Those are unfortunately not the only wobbles. From this perspective, I'd say the newly cut vertical features look great right out of the box. The horizontal surface finish left by the Z-axis, however, is pretty terrible. Yeah, I remember having spent a lot of time fine-tuning the Z-axis servo drive last time. It's having a hard time because of the uncompensated static load that is simply the weight of that axis. in combination with high-frequency cutting forces, which these servos have not yet experienced. Check out my real-time load bar graphs. If anybody is still left unimpressed by this delicious combination of LinuxCNC and CIA 402 servo drives, I don't know what else to say. This is how things are meant to be, clearly. Also check out how much the Z-axis is struggling just passively. 30% of the rated permanent torque, plus a bit of noise from the actual milling. The noise we will have to address in position control parameter tuning, and the static load will be eliminated with a gas spring counterbalance. One thing where Leadshine has a bit of work to do is cross-platform availability of their Motion Studio software. Don't get me wrong, I don't want a cloud smartphone AI version. Just Linux would be fine so that I don't have to get my hands dirty. In here we can use the one-click tuning program, which, if I may pedantically point that out, requires more than one click to perform a very complicated operation. So I guess it's fair to call it that. This tool should automatically move our axes and try to determine inertia and loop gains. You can specify a tolerance. 2 millirevolutions are suggested here. That would mean a 10 micrometer positioning tolerance in my machine. It lets you jog motors manually to set and test the range of motion in which tests will be performed. I still find it scary to just hand over all control over a motor that could accelerate 100 kg of steel to absolutely destructive velocities. Oh well, YOLO. I sure have my hand on the emergency stop. Oh, it's gentle enough at first, but does get a bit rough at the end. Alright, that went well. I'll let it do the same thing for all 3 axes, especially Z. And then we can take a judgmental look at a first surface finish sample. It doesn't matter much for this part, but I'm curious what such a set of auto-tuning parameters can do. It alright? The side walls are very good already, as expected. I don't even think there is a lot of potential for improvement there. The Z-axis is perfectly functional, but not pretty. I'll run the auto-tuning again with lower tolerance. And I'll use a brand new ball end mill for the final test piece today. A ball, or half one. This was an excessively long operation. This small thing took half an hour and 7 megabytes of G-code. I thought I was ready for a shiny showpiece a la Kern. A good attempt, but not quite there yet. We'll talk again once my gas spring is installed and my hip replacement business can start for real. Oh, and I haven't even mentioned the 4th axis yet. That is happening too. Until then, thank you for watching.